Let me introduce binomial theorem and generating function uh, for this Monday classroom. So for the next Monday, November 3rd, there will be a quiz on binomial theorem, uh, especially the binomial theorem for the integer n. That is a very fundamental theorem in discrete mathematics. But for the homework 4, we will introduce a generalized version of a binomial theorem. The generalized binomial theorem was invented by Isaac Newton, and he used this generalized binomial theorem to introduce differential calculus. In fact, the original binomial theorem is this one. This one. And in this case, the n and k are all integers. Okay, so if this is an integer, 1 plus x n, then this one can be expressed as the sum of this one. Okay, and this is n choose k, and that is by definition. What is n choose k? So n so to choose k from n set, there may be this many possibilities. The first, so suppose there are n many objects, and we want to select uh, k many subset. Okay, and then the first of all, there may be n many possibility to select the first one. Okay, and then since we selected already, n minus one many uh, set elements are left. So there may be n minus one possibility for selecting the second one. The third one is n minus two possibility, etc. And so the last one is n minus k plus one. Okay, so this is the first element, second element, and this is the nth element. Okay. So this must be n minus k plus one. But but in this case, there is a kind of ordering is involved because this is the first one, second one, third one, something like that. So for this case, selecting A first, B second, and C third is different from B first, A second, and C third, okay? But also C first, A, A, A second, and B third, okay? So also uh, B first, C second, A, this one is different, and also what? C first, B second, A third. This one is different. Also, this one is A first, and C second, B third. This one. So if the order is involved, this selection is different from that one. Okay, but we just uh, we just wanted to select three, in this case, three many element from the n set, then if we use a set notation, uh, This set is equal to, they are all the same. They are all the same. Okay. So if now order is not considered, they are the same one. Okay. So there are six many uh, set are all equals, and in fact this is a 3 factorial many mm, uh, sets are all one. So if the order is involved, so in this case there are n many uh, selections, and also this one is the order is involved. So we if we ignore ordering, then this one must be divided by uh, n factorial. Okay, n factorial. So this is n, because no, sorry, because we select k many element. So this one must k must be divided by k factorial. So in short, n choose k is n minus 1, n minus 2, and this is n minus k plus 1 divided by k minus 1. This is k factorial. 2, 1. Okay. So this is the, in fact, n choose k for if n is integers and k is also integer. But Newton generalized, find out that this one, this formula hold for uh, any any real number n, and also integer k. So, and also in this case, so n choose k, and he find out that n choose k also, if we use this one, then uh, this one also hold for any n. For examples, root 1 plus x is in fact 1 plus x 1 over 2. Okay. So in this case, the n is 1 over 2. Then this is 1 over 2. Then this n is 1 over 2. Okay. Then what is 1 over 2? Then uh, now we have this kind of problem happen. This is n is 1 over 2. Then what is 1 over 2? For example, now k is 0, 1, 2, 3, 4. So suppose this is 2. Then what is 2? But this is, there are 1 over 2 choose k, but there is no real meaning for this kind of selection. But the definition is just this one is n minus 1 up to n minus k plus 1, and the denominator is k factorial. So just use this definition. Now n is 1 over 2, so this is n, the k is 2. Okay, k is 2. So there, select 2. So this is n minus 1. Okay, select 2, and also this is 2 factorial. But by definition, this is by definition. Okay, select k many 1, and this is divided by 2 factorial. Then n is, this is 1 half. This is 1 half, and 1 half minus 1 is minus 1 half. Okay, minus 1 half, and this is 2 factorial. So using this definition, 1 over 2 choose 2 is this value. Okay, Newton find out this great fact. So just use the same definition, and then the binomial theorem or old style binomial theorem can be generalized for any real numbers and also integer k. That is Newton's uh, discovery, okay? And this is the key fact to open the door of modern calculus. It is very fascinating and very interesting and very important historical discovery, okay? So this is Newton's discovery. What happened? So there is internet speed. Okay, so the hold for any real number n, integer k, where this n choose k, this notation can be generalized for real numbers and integer k. Okay, so this is the Newton's binomial theorem, and then it was found out soon. The Taylor around, I think this is around 17040, maybe two, something like that. This Newton's generalized binomial theorem is invented around 166. Maybe this one, okay? And so uh, almost more than 50 years left. And Taylor is a mathematician. Taylor's introduced Taylor series, but this Taylor series is in fact exactly equal to Newton's binomial theorem. From Newton's binomial theorem, he derived this kind of uh, summation. So I think this is okay. This one. So there is a kind of uh, internet speed problem. This one. Mm. So Newton. Oh, sorry. So why? What happened? There is okay. Um, anyway, so let's see. So for for example, this kind of thing, then one minus, suppose this is root, okay? This is 1 minus x 1/2. So using this binomial theorem, Newton's binomial theorem, from uh, Newton find out the root 1 minus x and the 1 minus to the 1/2 from this one can be expressed as the sum of this one, okay? And then Taylor's the summarize the this one. This one is in fact uh, this using the differentiation, and this is the coefficient. This coefficient is in fact equal to this one. Okay? So it's very interesting. Uh, Newton just find out the series summation using generalized binomial theorem. But the Taylor's summarize that this one is in fact can be expressed as the differentiation value and divided by n factorial, okay, something like that. So so they are the same. So Taylor just summarize this one, okay. So that is the reason why generalized binomial theorem is in fact a kind of a Taylor series. Okay? So it's interesting. So this kind of uh, relationship is very important in the history of mathematics, and that's the reason why this binomial theorem and generalized binomial theorem is one of the most important fact in discrete mathematics. Okay, so it's important to know to prove the classical old style. So this one is the binomial theorem for the integer n and k. Uh, I want the student to know how to prove the classical binomial theorem. Uh, but I know that generally there is a generalized binomial theorem is invented by Newton. But first of all, let's prove a classical old style binomial theorem. So in this case, we can prove old style binomial theorem using mathematical induction. So mathematical induction is a little bit related to recursive thinking and recursion in computer science. That's the reason why uh, we introduce mathematical induction uh, as a kind of recursive thinking. So it's important for students to understand this kind of uh, technique. Okay? So let's prove this one. Then to prove binomial theorem by induction, first of all, it's important. We first of all know the Pascal theorem. Okay, this one. So this is the Pascal identity. So first of all, let's introduce Pascal identity. The this is a Pascal triangle. 1 plus like this. So the Pascal triangle uh, is see this is okay, a plus b 0. This is 1. Okay. So this is so this n is 1. So let's think about a plus b to the n. Okay. So when n is 0, then you have only 1. But how about n is 1? N is 1. A plus b 1 is just a plus b. Then just consider the coefficient for a and a plus b, okay? The coefficient is 1, and coefficient is, this is 1 also. So this is the coefficient, okay? Now how about n plus 2? A plus b, now n is 2, then this one is a squared plus 2 times ab plus b squared. And then just consider the coefficient. The first one, coefficient is 1. The second one is 2. The third one is 1. So that is 1, 2, 1, like this. So the Pascal triangle, the numbers in Pascal triangles can be interpreted in this way, okay? But there is another way. This one is but all the different uh, interpretation are in fact all the same. So the the another interpretation is now consider n choose k. Okay, so as I said before, n choose k, choose k many value n minus k plus 1, and then this one is divided by k factorial. So this value. So and let's consider the coordinate of this coordinate for these Pascal triangles. So this one is the n coordinate, and this is the k coordinate, like this. So this one is the coordinate n is 0 and k is 0. So this one is 0, 0. There is one. How about this one? This one is now n coordinate is 2, then k coordinate is 1. So this value is, in fact, n is 2, k value is 2, choose 1. That is okay. How about this 4? This 4 is now n coordinate is 4 and k coordinate 3. So n choose k, now that n is 4 and k value is 3. So 4 choose 3, that is 4. So in this way. So if you think about the Pascal triangle uh, like this by assigning the coordinate for each position and n coordinate and k coordinate, and that value is n choose k. Okay. Then there is an interesting uh, relationship in Pascal triangle. So that is the Pascal identity. So let's talk about this. So, in Pascal triangles, there is very interesting uh, fact is in this one. So that means this value is the sum of the previous these two value. This one plus this one. Okay, so in this way, as you see from this uh, the image, so this one, so this kind of mm, pattern can be described as this one. So let this be n, this value is n choose k, n choose k. Then this is sum of star n. Let this be apple. Okay, apple. So now this one is n choose k. So this is coordinate is n. Then this coordinate is k n minus 1. And this coordinate is k. Then this coordinate is k minus 1. So the coordinate of this star is and this is n minus 1 and this is k minus 1. Okay, so this one is the value for this star. Now how about the apple? Apple is the the coordinate is n minus 1 coordinate, and this coordinate is k is this coordinate. So that is this one. Okay, so this kind of pattern can be expressed in this way, and this kind of pattern is called Pascal identity. This Pascal identity is used to prove the classical binomial theorem. And then first of all, let's prove Pascal identity first. Okay? Then there may be many, maybe we can present two uh, proof. The first one is just we know that n choose k is and n minus 1 up to n minus k plus 1 divided by k factorial. And this one can be expressed in this way. So the n factorials divided by, so this is k factorial. And so since this is 1, so must be divided by n minus k factorial. So this one is in fact equal to this one. Okay. So to prove this one, just find out this value, this one and this one value, and n minus 1 choose k minus 1 is by definition formula from this one, and then just try to uh, simplify this one. So in this case, so look at this n minus 1 factorial is the common factor. So n minus 1 going out first, and the left one is this one and this one, and then by simple calculation, we can find out this one is in fact equal to n minus k. So we prove this plus this one is n minus k. So this is the first proof. The second proof is you may use anyone. You may use this proof or other proof. If I ask you to prove Pascal identity, and the second one is more uh, combinatorial proof, and that is a kind of storytelling proof. So n choose k is the possible way to select. Now you have three. Suppose you have n set, and just select k many uh, subset. Okay, k many element from the original one, and then now we want to choose k many uh, element. Then there are two cases. The first two cases. Now the last one, n is chosen, so n is selected, and second case is n is not selected. Okay, so when n is selected, then you must select k minus one many more. Okay, more element from the one. So n is already selected. So the left out is n minus one. So n minus one. From this n minus one left out, you must choose k minus one many uh, element, and then and adding this one, then the total is k many value. Okay, so when n is selected, then this many way to select another k minus one element. But if any is not selected, the left out is n minus one. From this one, since n is not selected, you must choose k many element from this left out. Okay. So by combining the case n1 and 2, the n choose k is equal to this many one plus this many one. Okay. Because there are two possible ways. So in this way, you can prove Pascal identity. Now we are ready to prove the classical binomial theorem using this Pascal identity. And let's prove the binomial theorem. Let's use using this kind of Pascal identity. Okay. Using um, so in mathematical we will use the mathematical induction, and then we want to prove just uh, 1 plus x to the n. This one is equal to sigma and choose k. So now k is choose from 0 to n. Okay, so and this is okay, x to the k, like this. Okay, so and then in this case, the first of all, we must the we must prove n is 1. So this is the smallest possible case. So check for n minus 1. N is 1, okay? So 1 plus x, this 1, that is 1. Now n is 1 and k is 0 and k is 1 from this formula. So this is n. then you can see that this is 1 choose 0 is just this is 1, and 1 choose 1 is 1, so that is equal to 1. So the left one is equal to the right one. So now we prove the case when n is 1, okay? So this is the first step. And then the second step is now let's assume that this formula hold for up to n, okay? Up to n. Assume for, so n is 1, 2, 3, so up to n minus 1. Now up to n, let's assume that, assume this one hold for uh, when n is 1 up to n, okay? Now the the main part of the mathematical induction is now using this kind of assumption, let's prove the next number. Next number is n plus 1. Okay? N plus 1. Want to check for n plus 1. So we we will try to prove on this possible case, okay? This case. This case. And then the mathematical induction, if we can prove this one, then uh, by the mathematical induction, we can say this binomial theorem is true. Okay, so this is kind of algorithmic proof. So just prove when n is 1, assume for up to n, and then prove the case when for n plus 1. So this is a kind of a step-by-step uh, proof, but from mathematical point of view, this is always true. So uh, just follow this kind of step-by-step methodology, we can prove mathematical ideas. So, so by induction, let's prove uh, we assume that this one is true up to n. Then now we must prove for the case n plus 1, okay? So let's start with this one. Let's start with this one. And then our goal is to prove that this one is equal to this one, okay? So this is, look at this. This is n plus 1, and this is n plus 1, this is n plus 1. Now, we prove this is a kind of proof for n plus 1 case n plus 1. Now, from this one, now this red one, n plus 1 choose k is from Pascal identity. This one can be divided into two parts. So this red one can be replaced by this one by this one. Okay. So then, as you know, this is a plus b times c. Then this is ac plus bc. Okay. So this one times this one is this first case. Okay. This first case. And choose k, this red one is the second case. Okay. So now we can have this kind of expansion. And then this part is important, but in this case, if the x is, so this, look at this, sigma, and choose k minus 1 xk. If the x is going out, then this one must be x minus k minus 1, okay? Because multiplying this one and this one, you have x to the kth power. So if x is going out like this, then this one must be x to the k minus 1, okay? And this coefficient is the same like this. And the second one is, okay, then let's see. Then let's k minus 1. This k minus 1 be, let this be apple. This is apple, okay? Let this be apple. Then the the k value is 0. So so in fact, this one is can be replaced by apple like this, okay? And then this is apple value is, so it's a little bit more difficult, but this is kind of mathematical uh, ideas. But so now this k minus 1 is equal to this exponent. Then let's use uh, k variable. Use the k variable. Okay. So I mean so so and choose, this is a kind of mathematical notation. Minus 1 x k minus 1 from k is 0 m plus 1. Then this one can be expressed as, let k minus 1 be, let this be apple, okay? K minus 1 is a kind of apple. Then this one can be, so the smallest value, the k is 0. If this k is 0, the starting apple value is minus 1, okay? The starting value apple. So this one is equal to apple is minus 1 to the n plus 1. This n choose, this is apple, and x, this is apple, okay? So look at this. So we can use this kind of, this is equal to this one, okay? We just use, replace variable k by apple, k minus 1 by apple. So this is the same. Then it is a mathematical notation. This apple maybe you may use the star variable. So you may use any variable. So the a variable, you may use a variable. It doesn't matter. Then why not k? So let's use k variable. So in this case, you must not be confused with this one, okay? But but this apple, so they are all the same. So let this be k, and this is k, and this is k. Because you may use apple or star or any variable, okay? But this k minus 1 uh, is not meaningful, because this one is must start with always 0, okay? So that's the reason why we can say this one. This one can be rewritten as this kind of notation. Okay, so this k minus 1 is disappears. Instead, we can use k like this. Okay, and then look at this. N choose k, x to the k. Look at n choose k, x to k. So they are the same. This is a common factor. Okay, common factor. Also, so this is a common factor, and there is x is there, and there is 1 times x plus 1. So you can combine those two part using this kind of multiplication. So this is x plus 1. And what is this? We already assume this one is hold for the case n. Okay, so this is n choose k. So this one is equal to this one, because by the assumption, by our previous assumption. So this one is equal to this one. So finally, there is 1 plus x and 1 plus to the nth power, and the result is 1 plus the n plus 1 power. Okay. So we can prove this one in this way. So this is a very short, but uh, inside of this proof, the basic ideas of mathematical induction is hidden in this kind of proof. Also, using this kind of Pascal identity and the process of mathematical induction, we can prove this one in this way. So it's important for you to memorize and to understand this kind of uh, proof technique for proof methodology for the case when uh, we prove the binomial theorem. Because, as I already mentioned, this this kind of classical binomial theorem can be generalized into Newton's generalized version and like this. And then this generalized version is, is in fact equal to Taylor series. So there is a very important relationship between Newton's binomial theorem and the calculus in this way. And so lots of calculus can be reinterpreted in terms of discrete mathematical thinking, okay, like this, okay? So that is, and also like using this kind of thing. So it's very, very important. After that, also the binomial theorem is also important because we can introduce a generating function, and then generating function is a very important concept in discrete mathematics and mathematics also, statistic and probability. So it's very, the binomial theorem is a very, very important concept for many parts. So let's introduce the concept of generating function using binomial theorem also, okay? So now we know the binomial theorem. Then from this one, we can introduce the concept of generating function. So for example, uh, so this is one, okay, one, one, one minus x. Then what is this? 1 over 1 minus x. Okay. And then there may be this 1 over and divided by 1. Then this is 1, 1 minus x. And look at this. This is minus minus. This is plus x. From this one, from this long division, like this, x minus x squared, minus 1, then this cancel out. This minus minus, this is x squared. And also you can use x squared like this. So 1 over x is, using this kind of long division, this one is equal to this kind of thing, okay? But using binomial theorem, this is 1 minus x to the minus 1, okay? And then using binomial theorem, you can also have this kind of thing. Also, if you use, this is f of x, using the Taylor series, you have the same result. So there are three possible methods to generate this kind of what power series uh, expansion. Okay. So in this case, we say 1 minus x. This is so 1 minus x. Then there is a power series, and then just consider the coefficient 1, and this is 1 and 1. So in fact, from 1 minus x to the 1, and there is a kind of correspondence is uh, okay, and 1, 1, 1, 1, something like that. But how about 1 minus x the x, okay? And then this is, there is x, so this is 1 plus x squared plus x cubed, something like that. Then by multiplying x, this one, x squared and x cubed in this way, okay? Then how about x 1 minus x squared? Then you have this kind of thing. So from this uh, from this function, you can have this kind of uh, series summation, power series, and then power series can be uh, described as a sequence of the coefficient. So in fact, this is the x coordinate, and this is the number code. Number is in fact is zero, okay, like this. In this case, the this is the x variable, and this is the first one is zero. Then you can interpret this series as a sequence of integer like this. So the coefficient of x squared is one, coefficient of one. Also the second one is zero. The coefficient of x is one. The coefficient of x squared is two. Coefficient of x cubed is three, like this. And also this one is 0, 1, 4, 9, 16, something like that. So there is a kind of a correspondence. This is the function, and this is the sequence of the integer. But this is sequence of integer is in fact uh, what happened? This one is in fact this sequence is coming from this power series. Okay, this power series summation. Sorry. So there is a the internet speed. There is a kind of speed internet problem. So it's hard for me to give a kind of well-designed lectures. So anyway, so uh, we say from this binomial theorem, we can generate this kind of series, and from this series, uh, we can have the coefficient of zero, and this is one, one, one. So there is a correspondence between uh, this one and for the sequence, okay? And then let's consider the other direction, this direction. Suppose you have a kind of this sequence, then what is the original function? Okay, original function. Then in this case, we say the generating function for this sequence is this one. Okay, so this is kind of a inverse relation. So in calculus, you have a differentiation, and then integration is the kind of a reversed the procedure. Likewise, from binomial theorem, you can generate the right hand side one from the left one. But now when we want to introduce the kind of a generating the concept of generating function, then the generating function is now from this sequence of integer, and in fact this sequence of integer is related to the this kind of power series. Then the generating function is from this one, just find out the original function. So in this case, generating function for this sequence 1 1 1 1 is this is one is the and this what is it? This 1 1 1 is in fact 1 plus x squared plus x cubed plus something like that. Okay, but this one can be derived from this function. Okay, so generating function of for this sequence is 1 minus x, 1 over 1 minus x. Then how about generating function in 1, 2, 3, 4? You can like this. This one is in fact this is 1 plus 2 is the coordinate of x, and the 3 is the coordinate of x squared like this. This is 4x cubed, something like that. Okay. Then what it is, this one is, in fact, this is 1 minus x squared minus 1, like this. So anyway, so generating function is a kind of a concept, a kind of reversed concept for binomial theorem. So in short, from binomial theorem, you from this function, you have a kind of this kind of power series, and you have a sequence. When we consider the reversed procedure, then from this sequence, now you can have this kind of power series, and then you can get the original function. Okay, so uh, in in calculus, from the original function, you can find out the derivative. Okay. So this is a kind of a differentiation, but from this derivative, when you can find out the original one, and this is related to integration. Okay, so there is that kind of relation. The binomial theorem and generating function is also a kind of uh, reversed procedure. Okay, thank you for uh, your attention.